So let's look at the duality of the Fourier transform. We touched this in a previous video, but we'll go through it in a little bit more detail here. Now the duality really comes about due to the symmetry of the function e to the I omega t. So forgetting about the actual values here, we'll just look at the shapes of the Fourier transforms. If we start off with a function here which is a value of 1, then we find the Fourier transform of that function, which is an impulse in the frequency domain. If we take the answer to this and then we Fourier transform it once again, so in effect we're taking this function here and putting this into the time domain and doing the Fourier transform, then we get back to the original function here, which is just a straight line. But there's a difference that has actually been scaled by a factor of 2 pi, but the other major difference here is it's actually flipped in the I omega axis. So although you don't see this here because it happens to be an even function, but this line here in effect has been flipped over onto this one, and this line here has been flipped over onto that one there. So we get the Fourier transform pairs. If we had a function x of t gave us a function in the frequency domain of x of I omega, then we could say the same function x of I t would give us a function of 2 pi x of minus I omega. So this is the flip here. So let's look at this in a bit more detail in terms of an analytic derivation. So let's look at the idea of duality analytically. Now before we go through this little bit of analysis, we'll go and simplify what we had above. So what we want to be able to do is distinguish between this I omega axis and this I omega axis, and also this t axis and this t axis. So what we're going to do is we introduce a little dummy variable. Instead of using this omega for this axis, we'll use the value of lambda. And again, when this frequency signal comes down here, it becomes a time signal. So we replace the time here with the lambda. So at this point here, lambda is frequency, but when we shift it down here, lambda becomes time. Now all we have up here is the Fourier transform from x of t to x of I omega. So we go through the first Fourier transform here, and then we take this function here and we change it to a time domain function, but it's the same shape, it's the same, ostensibly the same function. And when we do the Fourier transform again, we get back to this function here, which is the same as this type of function, but there's certain differences. So we've seen that before in just a second ago. So let's have a wee look and see how this is done. We're going from our time domain through a Fourier transform to a frequency domain. We're then taking this signal here and we're putting it back into another Fourier transform. We're calling it a time domain signal, and we're doing the Fourier transform to give us our frequency domain again. So all we're going to do is, we know that we're going to finish up with this x of I omega. So this x of I lambda, well that's nothing other than this x of I lambda here. So we can take this whole section here and put it in here, and that's what I've done there. Okay, so we're left with this line. Now we can take the x of t out of the integral sign here, and we'll have an integral from minus infinity to infinity of x of t, and we'll have a dt at the end. Now everything that's in the centre here, the integral from minus infinity to infinity of 1 times e to the minus I lambda omega t plus d lambda, well we've seen that before. That's really just the Fourier transform of a value of 1. Now the Fourier transform of 1 is 2 pi delta omega, but it's not quite the Fourier transform of 1 because it's actually omega plus t. Okay, so it's actually going to be 2 pi delta omega plus t. So from that we're left with this little equation here, integral from minus infinity to infinity over x of t 2 pi delta omega plus t by dt. Now this here is nothing other than the shifting property which we've seen in previous videos. So equivalently we can rewrite this as 2 pi x of minus I omega. So you'll note that this here is just the shifting property we've seen in previous videos. The only difference is we've got our delta omega plus t as opposed to a delta omega minus t. So it means that this whole thing here is just equivalent to our function x at minus I omega as opposed to the plus I omega. So we get this Fourier transform pair, that x of I t, Fourier transform was 2 pi x of minus I omega. So as a reminder here, whenever we do the Fourier transform of a function twice, we get back to the original function. It's scaled by a factor of 2 pi, and it's also flipped over in the y-axis, so that this side here becomes this side and this side becomes that side. So it's a mirror image on the y-axis. So that's all there is for the duality. I'll get you on the next video. Goodbye.